All right, so pH. This is going to explain to those of you who are maybe lifeguards during the summer or have a pool at your house. This is going to explain some stuff to you, maybe, possibly, as far as how the pH of a solution works. pH of a pool is kind of an important thing. As human beings, it's not good for us if we take a bath in water that is too acidic or water that is too basic. Okay, either way it can kind of mess with our skin. So when you're swimming in a pool, you want to make sure the pH is just right. Okay, so this is kind of applicable. So we need to talk a little bit more about solutions here for a second, and then we'll get into the pH part of this. You guys have your notes out? You need a second? Let me get these out so I can see what you're looking at here. We are on Roman numeral 3. Roman numeral 3, okay? All right. So, this is a little weird, okay? But when water is by itself, well, okay, let me ask you this. Does water conduct electricity?
Yes.
What do you think? Yes?
When it has ions in it.
Okay, you got that backwards, actually. So purified water does not conduct electricity at all. Okay? It's a very, well, I shouldn't say at all. It's a very, 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 very poor conductor of electricity. Okay? And the reason for that is in order to have conduction of electricity, you need some ions that can move around. In pure water, there really are almost no ions in that water. Okay? Now, why is it then that you always see these, like, you know, don't plug something in while you're wet, or, you know, don't drop your toaster into the bathtub while you're in it, that sort of thing? Why is it that that's a danger if water doesn't conduct electricity? Tap water does conduct electricity, right? Tap water has ions in it, okay? And even if the tap water didn't, so you think you're safe if you pour jugs of distilled water into your bathtub, then get in? As soon as you get in the bathtub, there's ions all over your skin, right? That's going to dissolve in the water, and now the water conducts electricity. So you can't get away from it, all right? So that's why they still make you get out of the pool when there's lightning in the summertime, because that water, with all those people in it, with all those chemicals in it, there are ions, lots of ions floating around in that water, and if lightning hits the pool, it will travel through the water to you, okay? So that's, when I say water doesn't conduct electricity, you need to understand that I mean pure water does not conduct electricity. But water with stuff in it does, all right? Now, even in pure water, there is a little bit of ionization that happens, okay? Every once in a while, this water, for whatever reason, will break apart into H plus and OH minus, just a little bit, okay? Now, I'm lying to you a little bit here. If you go into AP chemistry, you're going to learn really this H plus goes and connects to another water and makes H3O plus, which is called hydronium. But for our purposes here, you just kind of think of it like this, okay? Every once in a while, in a sample of pure water, this happens, where water just kind of splits apart. It ionizes, okay? The self-ionization of water. But it doesn't happen very often, okay? In fact, it happens about 1 in every 10 billion water molecules, okay? So, again, not very often at all. That's why water doesn't conduct electricity very well. But even when water ionizes, if you think about it, the number of H plus and the number of OH minus ions are equal, right? Because for every water molecule that breaks apart, you're going to have an H plus and an OH minus, okay? So because those H plus and OH minus ions are equal, the pH is going to be 7. That's why water is exactly neutral, because it turns out pH is determined by how much H plus or how much OH minus you have floating around in your solution, okay? If you have more H plus than OH minus, you're going to have a low pH. It's going to be acidic. If you have more OH minus than H plus, then you're going to have a high pH. It's going to be basic. All right, and that kind of fits with what we talked about the last couple of days, because remember, I've told you acids usually have hydrogen on the front of them, right? Well, what's going to happen if you put HCl into water? What do you think it might do? It's not going to explode. It's going to split apart. Okay? So then you have H plus and Cl minus. Okay? So this H plus makes the solution acidic. That's why HCl is an acid. If you put sodium hydroxide, NaOH, into water, what do you think is going to happen? I'll give you a hint. It's very similar to what happened over here. Yeah, these split apart, right? So now you've got Na plus and OH minus. So sodium hydroxide is a base because it makes more OH minus in the solution. Does that make sense? Something's an acid if it increases the H plus concentration. Something's a base if it increases the OH minus concentration. By the way, you guys familiar with sodium hydroxide? You may know it by another name. Have you ever heard of lye before?
Yeah.
Lye, used to make soap. Okay? You guys seen Fight Club? That's the stuff that he puts on his hand. Okay? That lye. So bases are not very good for you either, right? Because they can start to eat through your skin. So that's sodium hydroxide. All right, so acidic solutions contain more H plus ions than OH minus. That's what I just basically told you. And then basic solutions would have more OH minus than H plus. Keep everything organized here. Okay, everybody good so far? So now we're going to talk about what is pH, okay? Well, pH is the negative log of the H plus concentration. How many of you have done logarithms in your math class? Yeah. I've got good news for you. You don't have to understand them to be able to do this. All you have to do is be able to punch them in on your calculator, all right? So everybody take a look at your calculator for a second. Hopefully you have one with you. Logs? Yeah. Yeah, in math class, you actually have to understand what a log is and a natural log. In here, you just have to be able to use it, okay? Okay, so find the log button on your calculator. It will say L-O-G. That's how you find it. It's really not, I promise. Well, I don't promise. But it's like everything with chemistry, right? Chemistry is that... Chemistry, have we talked about this? It's the Wizard of Oz. Have we talked about this before? Yeah. My Wizard of Oz theory, I think I've said this before. Chemistry is the Wizard of Oz, right? Sounds really scary. But then you pull back the curtain and it's just this little guy talking into a microphone, right? Yeah, it's really not that bad, okay? So again, this looks scary, but it's really not, okay? All you have to do is type in, on your calculator, you literally just have to type in the negative, and then the log button, and then whatever your H plus concentration is. Now, on some of your calculators, the order may be flipped. You may have to punch in the number first and then hit the log button, and then it will take the log of whatever number you had punched in before, okay? But that's how you determine the pH. Okay, so the pH comes from the H plus concentration in the solution. That's what these brackets mean. That means concentration. Now, in the last unit, how did we measure concentration? What was the main way that we used to measure concentration? You remember? We had several different ways. We did percent by mass, percent by volume. Molarity was the big one that we used, right? Okay? So what this means is the molarity of H plus in a solution, okay? So the number of moles of H plus per liter of solution is what that really means, okay? So we can calculate a pH value if we know the concentration of H plus, or the molarity of the H plus in the solution. Do you guys have to write that down? Okay. All right. So neutral pH is 7. We already talked about that. Water, pure water, has a pH of 7. That's kind of our reference point. Okay? The scale goes from 0 to 14. That's kind of a lie. There are negative pHs and there are pHs higher than 14, but these are the ones that we typically experience. Okay? Anywhere from 0 to 14. Just to give you an idea of where some things fall on this scale. Battery acid is about a pH of 0. Sulfuric acid, pH of 1. Lemon juice and vinegar have a pH of about 2. That's fairly acidic, right? And we eat those. So once you get up to a pH of about 2, 3, somewhere in there, you can actually, your body can handle those, okay? The stomach acid in your stomach, is that on here? Doesn't look like it is. Is it over on this one? Okay, here we go. Yeah, gastric acid. It's about a 2, okay? Maybe a little bit less than a 2. So the stomach acid in your stomach, that's actually hydrochloric acid, the stuff that digests your food, usually around a pH of 1 or 2, okay? If it gets more acidic than that, do you know what happens sometimes? Well, you can throw up. That can happen. If it's, more acidic than it should be for a long period of time, you can start to get stomach ulcers, okay? Because what's happening there is the acid is starting to actually eat through the lining of your stomach, okay? So, but if your stomach's not acidic enough, then it's not able to digest your food the way that it's supposed to. So the pH in your body is really, really important, okay? Let's see, what else? Do they have blood on here? I can't remember exactly what blood is. Urine and saliva is right around a 6 or a 7, which kind of makes sense. So, well, maybe not so much for urine necessarily, but saliva would probably need to be a little bit acidic to help you start to digest your food as you eat it, right? Okay, so you can kind of see how this is related to our bodies. Orange juice and soda, pH of 3. You can put, I've never tried this before, but I've read this online. You can put a baby tooth into like a beaker or a cup of soda, leave it overnight, and the tooth is gone the next morning, okay? Soda is fairly acidic, right? So if you need a reason to stop drinking soda, that would be one. It's bad for your teeth. Not that you're going to, like, let it sit on your teeth for a 24-hour period, but if you did, it would really damage your teeth. All fish die at a pH of 4.2. That's an interesting fact to know. So you don't, that's the problem with acid rain, right? Because acid rain is rain that has a pH of about 4.2 to 4.4. So you get a lake that becomes too acidic, now all the wildlife dies. Bananas are about 5. Clean rain is about 5.6. So even clean rain is still a little bit acidic, right? But not too bad. Healthy lake would have a pH of about 6.5. Rainbow trout begin to die around 6.0, pH of 6.0. So you can see over here some of the things that would die if the pH gets too low. Milk is right at neutral. It's just barely acidic. Seawater is a little bit basic. So are eggs. Baking soda is a little bit basic. We talked about that yesterday because that's one of the things that tastes bitter when you eat it. Milk of magnesia has a pH of 10. Now, do you guys know what milk of magnesia is? Well, then what is it? Okay. Well, I feel comfortable saying what it is. It's something you take when you have stomach issues, right? Because what can happen here is your stomach is a little too acidic. You take the milk of magnesia, which is basic, that can help to neutralize some of that stomach acid, and now your stomach's back to the pH it should be. I don't know why that was uncomfortable for you to talk about. Ammonia is a pH of 11. Okay, so now we're getting pretty basic. Now we're getting into the stuff you don't really want to ingest, right? Soapy water, pH of 12. Bleach, pH of 13. Liquid drain cleaner, now we're at a pH of 14. Okay, so like I said yesterday, a lot of the things that you have, like household cleaners that you have, are going to be fairly basic. Okay, and those are very damaging to you if you ingest them. Okay, trying to see if there's anything else on this list that. It's about the same. I don't know why they put hydrochloric acid there. It depends on the concentration of hydrochloric acid. So, coffee is around a 5.5 or a 6, so slightly acidic, but not as bad as soda. So there you go. All right. So here's how you calculate pH. Solution has a hydrogen ion concentration of 3.5 times 10 to the negative 7th. what is the pH of the solution, okay? So here you just need to know the formula for pH, right? pH equals negative log of whatever the concentration is, okay? In this case, the concentration is 3.5 times 10 to the negative 7th. Okay, the hardest part about these problems is just putting this into your calculator. So, the way that you would type this in on most of your calculators, now it may be different for some of you, you would put the negative log, and then a lot of times when you punch the log button, it will actually bring up the parentheses for you, and you just type in 3.5 EE negative 7, okay, whatever your exponent key is. Hit enter, and it should give you a pH. Okay, so it's just basically typing it into the calculator. Okay, sig figs are weird with pH, so I'm going to be very lenient here. Technically, whatever number is before the decimal point doesn't count for significant figures on a pH. It's just, so you would need two numbers after the decimal. Yeah, because there's two sig figs here, so you'd need two numbers after the decimal, which is a little weird. Again, I'm not going to be real strict on the sig figs here. Yep. How to do it on your calculator. Okay, I'll take a look at it in just a second. The answer on this one, that sounds reasonable, 6.46. So, let's see, take negative log 5, 7, yeah, 6.46 should be the pH here. That's technically not 3 sig figs. That's what I'm saying. With pH, it's a little weird. If you rounded that to 6.5 because you saw two numbers here, that's fine. Okay. This, for whatever reason, I think I kind of know why. This is really kind of your exponent because we're talking about a logarithm here. So that doesn't really count as a sig fig. It's telling you what the exponent is, right? And then these two numbers are the ones that are actually significant. But I'm not too worried about that. Like I said, if you put 6.5, that's perfectly fine. Okay? All right. Example 2. What is the pH of a 1.24 times 10 to the negative 4th molar hydrochloric acid solution? Okay, now, here we have to be a little bit careful. All right? This is a little tricky, and the only reason why is because it's not telling us the H plus concentration here. It's telling us the concentration of HCl. Okay? But let's think about this. If I have 1 mole of HCl, and then I put it into water, and it splits up into H plus and Cl minus, now how many moles of H plus do I have? We've talked about this before, and actually I could write it as an equation, right? So HCl splits up into H plus Cl minus. If I have 1 mole of HCl, then how many moles of H plus do I have? 1. It's just a balanced chemical equation, right? There's a 1 here, a 1 here, and a 1 here. Okay? So if I have 1.24 times 10 to the negative 4th molar HCl, then I also have 1.24 times 10 to the negative 4th molar H plus, because they're a 1-to-1 mole ratio. All right? So I wouldn't worry too much about that, but I just wanted to show that to you. So to figure out the pH of this one, again, it's just the negative log of the H plus concentration, which we just said is 1.24 times 10 to the negative 4th. You punch that into your calculator. Anybody have that one?
You can have an exponent under the log. So.
Oh, okay. So put log 10 because this is a log base 10. That is weird. Okay, let me look at it. Okay, yeah, on yours you'd have to type in the number first and then hit the log button. Like if you hit 23 and then hit log, then it will give you the log of that number. So put in the number first, then hit the log button. And then make it a negative, which will actually change it to a positive. Okay, so what are we getting for this one? 3.907. Good job on the sig figs there, but 3.91 would be perfectly acceptable. All right. Now, let me show you something here that might help you check your work a little bit. 1 times 10 to the negative 7th is, well, I'll tell you what. Everyone punch that into your calculator. What's the negative log of 1 times 10 to the negative 7th? What is the negative log of 1 times 10 to the negative 7th? It should be 7. Yeah. Negative log of 1 times 10 to the negative 7th is 7, okay? So, here, watch this. Negative log of this is 7. Negative log of 1 times 10 to the negative 4th is 4. Negative log of 1 times 10 to the negative 10th is 10. You seeing a pattern here? Okay? So whatever your exponent is, your pH is probably going to be fairly close to that exponent. When you type in 1 times 10 to the negative 10th and take the negative log of it. You're typing in 1 times 10 to the negative 10th wrong then. You need to type in 1 and then your exponent and then negative 10. Don't put a times sign or a times 10 or anything like that, okay? And then it should give you a 10. But here's my point, okay? If you see this right here, 1.24 times 10 to the negative 4th, if your pH is pretty close to 4, then you probably punched it into your calculator right. Does that make sense? Okay? Now, it's not exactly 4 because of this number in front. If this was 1 times 10 to the negative 4th, this pH would be exactly 4. Okay? So just something you can kind of look at to make sure you're on the right track. Okay, another example here. How are we doing on time? Not great. Okay, so this will be the last one we do today, and then we'll have to finish these up tomorrow, or Monday. Okay, so we've got 735 liters of a solution that contains 0.34 moles of HNO3. Well, again, pH is the negative log of the H plus concentration, right? You know what? Last 3 minutes on a Friday is probably not a good time to do this problem. We'll do this first thing on Monday, okay?